let's talk a little bit more about some more specific things about significant figures. So I did mention that usually zeros in a measurement are considered to be placeholders, not usually considered to be significant. Well, that is not always the case. There are sometimes that zeros do matter. And we're going to talk about the rules first, and then I'm going to talk about the scenarios in which you can get these. So here are a couple of, here are the main rules of what numbers in a measured quantity are significant and which ones are just placeholders. So for the sake of convention, what I've done is the following thing. Anything that is a placeholder, I've highlighted in blue. Anything that is a significant figure, I've highlighted in green. And the guess, well, I've highlighted in red. All right, so our very first rule is the non-zero rule. So in the non-zero rule, that means anything that's not a zero is automatically significant. So here, 5 and the 4 are the only non-zeros, so we have 2 significant figures, and that's the non-zero rule. So when we take a look at this, 987, 3 significant figures, right? Those first 2 significant figures are very reliable, and the last digit, the last significant figure is a guess. Over here, 0.0000, 59869. These zeros are all placeholders, and these are the only significant digits, and there are 5 of them. 1, 2, 3, 4 that are very reliable, and then of course our guess. And then this number here, well, there is only 1 significant figure, and that is our guess. So right away we know that the instrument used to measure this was low quality, because these zeros are all just placeholders. And then finally, same thing here. These zeros here, placeholders, and then there's 1 significant figure there. All right, so the non-zero rule, that's the easy one. But sometimes zeros are significant. And this is where we get into what I like to call the zero sandwich. Now, these are not actually the technical names for any of these techniques, mostly because I don't know what the actual technical names are. So these are the nicknames I give as a means of helping to remember. So the zero sandwich, the idea is this, is any zero sandwiched in between non-zeros are considered to be significant. So let's take a look here. So here we have a 0, but that's sandwiched in between a non-zero and a non-zero here. So that 0 is considered to be significant. And these zeros over here, they're again just placeholders. So that's why we have a total of 5 sig figs, including this sandwiched 0. Now over here in this one, we have a double-decker 0 sandwich. Equally low calorie. 1, 2, 3, 4, 5, 6, 7 sig figs. These 2 zeros again are placeholders. Now we have a triple 0 sandwich, right? Non-zero, 0, non-zero, non-zero, 2 zeros in a row, and then a bunch of non-zeros. So all of these between the 1 and the 7 are considered to be significant, and that last 0 is just a placeholder. So that's 1, 2, 3, 4, 5, 6, 7, 8, and that's how you get those values. So all of those numbers were produced from the measurement itself. Next, we're going to talk about the next rule, which I refer to as the weird rule. So let's talk about what I mean, what this very bizarre name is. Okay, so now we're going to talk about what happens when we have extra zeros. So sometimes extra zeros to the right of the decimal point. If you have an extra 0 after a decimal point, it's kind of redundant. So for example, if you want to represent the number 200, all you need are 3 numerical digits, and that is a 2 followed by 2 zeros. That's all you need to represent 200. However, if you record it as 200.0, that 0 there, right, it seems a little bit redundant, all right? So that redundant 0 doesn't actually need to be there to represent 200 per se. You should only need these 3. So if this 0 is actually there, it must be there for a reason. And that means that it was part of the measurement. And specifically, what that means is that is actually the guess. That last 0 must have been our guess, which meant that when we measured it up, it must have lined up exactly on that line, right? It must have landed on the scale. So that would have been our guess. So when you see that last little weird trailing 0 after the decimal point, we consider that to be significant. So now, that means if that's significant, so if this is significant, and of course that's a non-zero, that's significant, that means all of these are also significant. So in this case, this 200.0, based by looking at it, everything's significant, so that would be 4 sig figs. That's how many sig figs this one would. All right, so let's take a look at some examples here. So let's start off with our first one, 100. Based on the way it's written, now I made a little goof on my note. That 1 is the wrong color. And I'm going to have to modify my note after the fact. So if I was to do this properly, I'm going to scratch that out. That should be 100, like that. Now the reason why is because that 1 is just a guess. There's only one sig fig. So I made a small mistake, but we've corrected it for now in the video at least. So that is our guess. Those 2 zeros are just placeholders. So now let's take a look at this next number. So when we have 100.0, okay, I've color coded it properly this time. That 0 is weird. Normally you wouldn't have it there, but since it's there, it must be significant. So that's a significant digit. Obviously this 1 is a significant digit. So we've got 2 rules. We've got the weird rule, which is that 0 thing, and the 0 sandwich. So in this case, all 4 digits are considered to be significant. Now let's take a look at the last example here. So we've got 0.000090. So these zeros all here, just placeholders. That 0, that's kind of weird. You don't normally put that there, so that must mean that it's significant, and it's also the guess. And then, of course, the 9 is non-zero. We have 2 sig figs. And that's it for that particular rule there. Fairly straightforward. And then the last rule that we need to talk about, and this one I affectionately refer to as the vague rule. Okay, so sometimes what happens is the vague rule is actually related to the weird rule. And the problem occurs is when we have a 0 that is a guess and we do a conversion. So let's take a look at this example over here. Let's say we had this measurement that we got 2.40. So when we made this measurement, we believe that it landed right on the decimeter line. So our guess was 0. So that 0 is our guess. And that means the 2, the 4, and the 0 are considered to be significant. And the reason why the 0 is considered significant, because you wouldn't normally have it there after the decimal point. It's not necessary to be there to represent 2.4. So that 0 at the end must be significant. So what happens if we convert it from centimeters to meters? From meters to centimeters. So we want to convert this to centimeters. So we multiply by 100. Well, when we do that, we get this number right here. Well, here's the problem. If you look, based on the way we've drawn it, it looks like the 4 is the guess, and looks like the 2 is the next digit over. So it only looks like it has 2 sig figs. But we know that this 0 here, we know that that 0 is significant because it was significant over here. So we started off with 3 sig figs. We need to end with 3 sig figs. So the solution to this problem, when we have this vague situation, is we add a tilde. We add a tilde over top of that, that 0, that vague 0 there, this one right here. So by adding this tilde on top, that communicates to whoever is reading it is that that 0 is actually part of them. So that makes it significant, and that's how you deal with when you convert from the weird rule into a different scale. That's how you can indicate that the 0, some of the zeros are significant and some of them are just placeholders. So in this case, that 0 is significant, so we still have 3 sig figs. So let's take a look at some of my examples over here. So when we take a look at here, the way it's drawn here, I've got the tilde on this 0, so I know that that 0 there is part of the measurement. That is our guess. And of course, this is a non-zero, and these 2 zeros, well, that would be your 0 sandwich. So we have a total of 1, 2, 3, 4, 5, and that's where we get the 5 sig figs. These 2 zeros are just placeholders. And the last example over here, so we see that this 0 has a tilde on top, so that makes it significant. And of course, these are all non-zeros, so that's 1, 2, 3, 4, 5, 6, 7 sig figs, and that is all there is to it. All right, so again, this is why so this is explaining how we can identify which things are placeholders and which ones are not, which ones are significant. But again, why are some zeros considered just to be placeholders? Well, now let's take a look over here. So when we look at this example over here, let's say we measured something and we measured it and we got 3.5 meters. That means that the 5 is the guess and that 3, we're absolutely certain about that. So we have 2 digits that were generated. We're absolutely certain about the 3, and then the 5 was the guess. So this has a total of 2 sig figs. So now we can convert meters into millimeters to any other unit. So the conversion from meters to millimeters is multiplied by 1,000. So we've got 3.5 meters, and we multiply by 1,000, we get 3,500 millimeters. So when we do that, we have to recognize that the number of sig figs must remain. So that means that 5 is still our guess. That 3 is part of the measurement. It's a non-zero, and it's also very reliable. And these 2 zeros are just placeholders. They are not part of the measurement, so they can be ignored. So 2 sig figs, and that's why those are placeholders. So the next thing we need to talk about is the weird rule and the zero sandwich rule.